All right. Good afternoon, everyone, and welcome to our panel on decarbonizing aviation. For anyone watching on YouTube, feel free to ask questions and we'll copy them over to Zoom. I'm Mike Nietzsche, and I co-organized this panel with Carlos Diaz-Marin. We're both first-year graduate students in mechanical engineering at MIT. I'm super excited to introduce our moderator, Professor Venkat Viswanathan from the Department of Mechanical Engineering at Carnegie Mellon University. Dr. Viswanathan is a leading authority on electrification of semi-trucks and aviation. He has broad experience in materials related to lithium-ion batteries, as well as in next-generation technologies, such as solid-state batteries and lithium-air batteries. He's also an expert on autonomous electric vehicles. He has earned numerous research awards throughout his career, including the Alfred P. Sloan Fellowship, the Office of Naval Research Young Investigator Award, a National Science Foundation Career Award, and he was an MIT Technology Review Innovators Under 35 finalist. So, welcome, start.
Thanks, Mike, and I'm very excited to moderate this panel with a great group of people. I'm just going to set the stage with a few slides, which hopefully is coming through. So we're going to talk a little bit about decarbonizing aviation, and I sit in the mechanical engineering department at Carnegie Mellon, and also the Scott Institute for Energy Innovation. So the sort of question is, what is the sort of approach to decarbonizing aviation? And in that, there was a historic moment last year, December 10th. It was heralded as the third era in aviation, right? So Harbour Air, a seaplane company, made what would be called a historic first, where they ran an electric seaplane in Canada. And it's sort of an important moment where they took a 63-year-old seaplane that's shown here, and then they electrified it. And I think that's one possible route towards decarbonizing aviation. We're going to hear about a few other approaches as well from our panelists today. Now, these small planes are actually only a small piece of the puzzle, and so let's sort of take the bigger chunk of the aviation and the transportation sector. This is just a sort of quick snapshot of the CO2 emissions, which is one piece of the puzzle for what is needed to understand radiative forcing or global warming. Stephen Barrett's going to take a deeper dive in this. And if you sort of look at the pie chart of what sectors contribute to the CO2, light vehicles, right? And we've seen significant penetration around sort of notionally sustainable personal vehicles through electrification of personal vehicles, as well as combination with renewable sources of power for those vehicles. We're slowly starting to see penetration in the light commercial vehicles, right? So after all, pickup trucks are still the best-selling vehicles in North America. And then we're slowly starting to see things on the heavy-duty market, right? So there are offerings in electric semi-trucks. And although aviation in this sort of CO2 pie seems to be small, as we will see, as we will hear from the panelists, this is only a part of the puzzle in terms of understanding how that affects global warming. And so I think it's important to think about decarbonizing aviation, right? So I think it's an important topic, and I think it's very timely, and I'm glad the organizers have picked this as one of the sort of panels to talk about. Now, while the success of Harbour Air and other sort of smaller planes are significant, if you look at the fuel consumption, and we'll hear more about these kinds of things from our panelists, the important pie to attack are single aisle and twin aisle. Right? So those would be sort of the kind of aircrafts that you would fly for distances of the order of a few thousand kilometers. Now, if you sort of ask the question, what would it take to electrify something like a single aisle aircraft with whatever is your energy source, batteries or other kinds of electrical power sources such as fuel cells, you can analyze that as a function of the aircraft range, and you see something quite interesting. This is borrowed from a paper from Alan Epstein. And what you see is, depending on the kind of specific power you can deliver out of your battery packs, or other kinds of power sources. What's marked here is the needed specific energy or energy density. So that's how much energy you can store per weight of your power source, and the aircraft range. And what you see is that you see numbers in the order of a few thousand, right? Maybe some number between 1 and 5,000, and you can see that state of the art. This would be PRL9, so these would be the kind of batteries that would power your electric cars. They're not even on the chart, right? And so that's an important message, right? That the kind of energy sources we have are not adequate to address one approach, at least direct approach of electrifying aviation directly through batteries or other kinds of electrical power sources. Fuel cells also suffer from the fact that they may be able to meet the energy density requirement, but the specific power remains challenging, right? The best state-of-the-art fuel cells in Toyota Mirai still are well below this 3 kilowatt per kilogram mark. So there's a specific power challenge. Now, this is on the sort of the old aviation market, I would say. And if you sort of look ahead, right, this is a artist rendering from an Uber Elevate Summit where they show a concept around urban air mobility. And these are these sort of, so-called skyports, which would essentially have these kinds of vertical takeoff and landing aircraft that would come in and, take you from probably from the top of your building to where you would want to go, right? So the promise is that I could go from top of my house in Pittsburgh to to the Pittsburgh airport in like 10 minutes. And so it's very exciting, and depending on who you ask, there are at least 170 electric aviation concepts in this sort of vertical takeoff and landing. And the Vertical Flight Society pegs this at $1 billion of investment. And I think it's important, and we'll hear from some of the panelists who are working on this, on whether this is sort of, whether this hype is worth it or not, or what's the reality. So I'm very excited now to sort of turn this over to our panelists and get their perspectives. We have very exciting group of panelists from a broad range of experience from government, academia, and industry. And so I'm very excited first to turn over to Rodger Dyson, and hopefully you can take your, you can share the screen as I introduce you.
I will do that. Can you hear me?
Yep.
Okay, excellent.
So Rodger is at NASA Glenn Research, and he's been there for over 30 years, and he currently serves as the hybrid gas electric propulsion technical lead. And he's going to tell us first a little bit about sort of the challenges around electrifying aviation.
All right. Can you see that? Oops. All right. Can you see the screen?
Not yet.
Not yet.
All right, there we go.
Got it? Okay, excellent. Let me make that bigger. Sorry for the technical things. One of the interesting things about all this remote tools, we're probably using like 4 or 5 new tools that we normally don't use in our normal work days. So sorry about that. All right, well, thank you very much. I guess we're gonna do this in 2 sections. So I'll give an introduction to the areas of electric propulsion as it relates to decarbonizing aviation. NASA's focus is actually tackling the electric propulsion at these larger aircraft sizes as you had mentioned earlier, because that's the largest user of fuel. Overall, I don't think the previous slide showed this, but about 3% of the CO2 produced is from the from the aviation industry currently. So yeah, we're working actually the on-demand mobility market. There's a group that's working that. We have a group that's working the regional market, and then we have the single aisle as well. The single aisle work we've been doing for maybe 10 years or longer now, working our way up at least since 2008, some sugar studies as they're called. But the idea at the single aisle level is that's where you can have the highest impact on the fuel burn and therefore emission reductions. And the reason for electric propulsion in these other market spaces are typically for other reasons. For on-demand mobility, it's a new mobility capability. And then also for the regional market, it allows you to use the smaller airports. So in terms of having an impact on decarbonization of the environment, the single aisle is where you get the best return on investment right now. And that's where we have been investing. And I just want to highlight too that we actually have to design these systems so that that when you're saving the emissions, that you're also still have a vehicle that can fly, that's still robust, that can still be certified, because all of these technologies are adding weight and they're adding inefficiencies if not done in a coherent system way, integrated way. Turbofans have taken 50 or 60 years of maturity to develop to the point where now you only have 2 engines on an aircraft, and that's considered safe enough to fly across the Atlantic. Used to be you had to have more than 2 engines, and now we're entering that same phase with megawatt scale electric machines. And this chart I have in the bottom right here just kind of shows that if you fall below those lines, that you don't get a net system benefit, and if you're above those lines, then you do get a net system benefit, which means it drives our technology to new levels that just haven't been necessary before. We need, very high efficiency motors and very high efficiency machines. And when you look at the schedule for this, and when we're planning out what we're going to do over the next 20 or 30 years, we want to invest appropriately at the different levels. So the way it's going to work out, we believe, is urban air mobility, the smaller aircraft. NASA has the X-57 aircraft that's going to be flying soon. That's going to give you a base of technology that you can certify, get some endurance tests done with it, confirm it operates at altitude, things like that. And then we're planning maybe by 2025 range that you'd have single aisle aircraft which use the megawatt scale technology, and estimates are anywhere from 5 to 10% fuel savings. And then beyond that, where it's a radical redesign of the aircraft to support liquid hydrogen, for example, with a cryogenic aircraft. And then just real quickly, there's 100 years of electric aircraft work actually, but same thing with the automobile market. If you go to Henry Ford Museum in Michigan, you can see the same phenomenon that happened. Electric's great, but you need all the other technologies to support it, the energy storage, the efficiency, the mass, and so forth. So there was a good 100 years there where not a whole lot happened. And then since the year 2000 and on, there's been a lot of interest, predominantly because the power electronics technology has so radically improved, and we can now consider doing some of these things. And then I'll just close my introduction with the barriers that we're working: weight, efficiency, energy storage, high voltage, thermal management, flight controls, and safety and certification. And even at the urban air mobility, the FAA is wrestling with, well, how do you certify all these vehicles that have all these new technologies on it? And they have 170, 180 applicants. And I believe there's 2 of them that they may be approving, but only by using established technologies. So it's a challenging field going forward. And in my next set of slides, after we finish the introduction, I'll go into more details about how we're attacking each of these barriers.
Fantastic. Thank you so much, Rodger, for setting the context so well. Next, we'll have Stephen Barrett, who will sort of talk about the challenges in aviation as it pertains to how that affects radiative forcing and global warming. He's a faculty member at the Department of Aeronautics and Astronautics at MIT, where he leads the Laboratory for Aviation and the Environment, and also the MIT Electric Aircraft Initiative. So, Stephen, hopefully you can share after Rodger stops sharing.
Oh, I stopped sharing.
Thanks. I'm just trying to grant access to my Zoom. Actually, Venkat, maybe go on to the next presenter first because Zoom's not cooperating here.
All right, so maybe we'll try Ed's slide deck, and hopefully that works. So we'll do Ed Lovelace, who is a technical fellow at Boeing Aurora, and he leads their electric power systems, road mapping, strategy, technology development. In the sort of first part of his slide deck, he's going to tell us a little bit about Aurora and Boeing's efforts in electric aircraft, and then we'll take a deeper dive with him in the second phase around the exciting stuff that they're doing on urban air mobility.
Okay, so let me just check first. You see my full screen version? Is that right? Okay, good. All right, great. So thank you, Venkat, and thank you, other panelists, for inviting me here today, and of course for everyone making time on the webinar. So as mentioned, I work for Aurora Flight Sciences, and I also support the Boeing Next portfolio, which you'll see in a couple slides. And the area that I'm responsible for is all of the hybrid and full electric technology development applications. So that includes storage, generation, high voltage distribution, and propulsion. So let me just quickly move on here. All right, great. Just very quickly about Aurora for those of you who might be unfamiliar with us. Aurora has their roots at MIT, founded in the 80s. Following on a human-powered flight project that many of you may be familiar with, the Daedalus world record holder for human-powered flight. And that was what helped spawn the company to develop a business centered around designing, building, and flying innovative aircraft over the last 3 decades. And just over 2 years ago, we were acquired by Boeing, so we're now both supporting and leveraging the full capabilities of the Boeing enterprise. A lot of these aircraft and a lot of our technology background has been in clean aviation solutions. You'll see scattered throughout our history, solar aircraft, battery electric solutions, hybrid electric solutions. And this is a key part of our DNA that we've brought forward into the Boeing enterprise. So just talking again about the future markets that are part of this panel, which is looking at decarbonized solutions. Here you're looking at the Boeing Next portfolio. And Boeing Next was created by Boeing in order to develop some of these future disruptive mobility markets and look at new ways of moving through the air. And you can see a portfolio of platforms that we are in development and study on. And again, kind of the key underpinning elements of that are that all of these developments are centered around safe and sustainable future mobility solutions. And that goes from the small data and insight type of platforms to cargo platforms to passenger platforms. To be clear, this also spans a full range of target segments, from the short-range urban applications to regional and eventually to global applications. What you'll see in the second half when I go through some more of the challenges, I'm going to focus primarily on the urban air mobility, so the short-range metro city type of applications. Now, the way the Boeing Next team goes about this, we have a lot of internal development work that we're doing, but we also leverage partnerships and joint ventures. And you can see some of the joint ventures we have related to developing software platforms to enable AI-driven solutions and go beyond basic UTM traffic management systems. Partnership that we've created called WISC, that is leveraging the Cora passenger air vehicle platform that you can see above, and Arion, which is looking at supersonic future flight. So it was mentioned briefly that urban air mobility is a rapidly growing area, and for sure, there's an accelerating amount of activity in terms of startups that are involved in this area, as well as investments being made. And you're seeing, of course, lots of a wide range of projections on eventually how large this market might get, into the hundreds of billions. But in addition to the basic needs for this urban air mobility to be safe and clean, the other underpinning item that is needed for this to take off is it needs to save a consumer time. That's the main value that it has in this type of urban setting. Being able to connect new locations that haven't previously been served by traditional air transport, and doing it at a rate that saves them time. So as you talk about large urban centers growing over the coming decades, today you're already in some centers spending more than 90 minutes moving from a home to where your location is going to be for the day. That's only going to get worse. And so urban air mobility is an opportunity to be part of a multimodal system that'll save people time. So I'll stop here at this point, and then we'll go into some of the challenges on the second half.
All right, thanks a lot, Ed, for giving the Boeing take. Stephen, take 2 of yours. Okay, fantastic. We're up and running. So Stephen's going to set the context for the scale of the problem, how this pertains to radiative forcing and global warming.
Thanks very much. So I'll just start by noting that aviation is the fastest growing mode of transportation. So even before we start thinking about urban air mobility and other services in the future, already this is a massively growing industry, obviously putting aside the current issues the world faces right now. And to give you a sense of that, I'll show you a chart of data made at MIT, which shows fuel burn from civil aviation for the first 15 years of this century. And you can see here the tremendous rate of growth, which is at some 4 to 5% per year. Now, for comparison, the average efficiency improvements for commercial aviation is around 1 or 2% per year. So that tells you that the growth in aviation is far outstripping by a factor of several the increase in efficiency. Now, in terms of where those emissions occur, they currently occur mostly over the US and over Europe. But that's not necessarily where a lot of the growth in the world will be going forwards. If we take a look globally, you can see here longitude along the bottom there and fuel burn density on the y-axis, where around 90 degrees or so is here is the US, this is Europe, and this is Asia. What you can see here is that if you take the different years from 2000 to 2013, the growth rate in Asia has been absolutely tremendous compared to relatively flat signals in North America and Europe. And that's the kind of trend we expect to see going forward over the next several decades. And putting all this together, we think there'll be something like a factor of 2 or even 3 growth in civil aviation emissions and fuel burn by the middle of this century. Now that's challenging enough, especially when much of aviation wants to get to net zero emissions by 2050. But there's another gotcha for aviation, which is unique to the sector. Now, what I'll show you next is a chart that shows the warming or radiative forcing from aviation caused by the different emissions from the sector. This is the chart here. Radiative forcing at the bottom here is the measure of warming, and at the top there's carbon dioxide. Now, carbon dioxide gives you a certain amount of warming that is about 3% of warming for the whole world today. But if you look at the total here, you can see that that total is about double CO2 alone. In other words, there's a whole range of effects unique to aviation that occur because the emissions happen high up in the atmosphere that mean that aviation has roughly a factor of 2 uplift on the climate impact compared to the equivalent emissions at ground level. So all these factors mean that aviation faces a real challenge because it's very difficult to come up with an energy substitute for jet fuel. And then you've got this multiplier and you've got tremendous growth. And once you build an airplane that lasts for 30 years, and building and certifying airplanes takes a very long time. So all of these things mean we're really facing a huge challenge as an industry here.
Thanks a lot, Stephen, for setting the context. So I want to go back to Rodger and ask him to take us through the many challenges, right, that face electric aviation, and I think we can view all the challenges as opportunities for things that we should all be thinking about and working on. So Rodger, on to you for taking us through the challenges.
Well, thank you. I'm actually already learning interesting things from the panel myself, so hopefully everyone else is too. Yeah, so now I'm going to talk about how we're tackling, in particular, the megawatt scale type technologies that are required if we're going to replace or reduce the fuel that's used on the single aisle aircraft. And as indicated earlier, that's the bulk of the fuel that is used in aviation today are those size vehicles. But what we're finding is that it's an integration challenge. While you're transitioning from one technology to the next technology, and you have to do it in a safe way, that means you typically keep the legacy equipment on board while you're adding new equipment at the same time as backups and things like this. So there's a transition period where it actually is more challenging, and then eventually you can rely on your advanced technologies completely. But it boils down to there's a power, propulsion, thermal, and airframe integration challenge. And they're all interrelated. When we're talking, today single-aisle aircraft have been optimized over many decades because they're so widely used. So to improve them further is a real challenge. It's not an easy win. You might benefit one part of the system, but it costs you someplace else. And when you're talking about maybe net benefits of 5 to 10%, with all of these systems playing nicely together, it's easy to not see that net benefit if all of your technology doesn't perform as you're hoping. So we need to integrate all these technologies, improve fuel efficiency, emissions. The new thing is low-grade waste heat. Today's aircraft have about a 50 kilowatt heat load on them. Now we're talking about putting maybe a 300 kilowatt or higher heat load at low temperature because of all these electrical systems giving off heat throughout the vehicle. And we also would like to be able to reduce the vehicle mass, or certainly not increase it. So whether we take up volume or mass, that impacts the number of passengers you can put on the aircraft. So if you look at what's happening today in terms of, there's going to be a number of flight demonstrations you're going to be hearing about. I don't think all the companies have announced them yet, but the technology, in terms of the motor technology, people are using permanent magnet machines is a near-term technology that people are mostly using for flight because it's lightweight. And I have the airframe mnemonic on the side there where I'm showing that power, propulsion, and thermal all integrate together at the airframe. And then there's a whole set of enabling materials that actually raises the water for all of those different technologies. And we're actually tackling all of those different areas. So talking about integrating the electric motors, first of all, there's a couple of ways to do it. Industry right now is going towards, again, I'm talking about the large 150 passenger scale aircraft, single aisle, are going towards parallel hybrid. Because that involves the least change to the airframe, change is not your friend when it comes to these large aircraft and getting them certified. One crash and it changes your whole perspective. So they're very conservative, and by doing this approach where you embed electric machines with the turbofan, you can get 3 to 5% emission savings, fuel savings, which maybe doesn't sound like a lot, but again, because it's such a huge, it has a huge usage rate, and these systems are already so optimized, getting 3 or 5% is worth a lot. And it's billions of dollars and many gallons of fuel it's saved. So there's two ways to do it. Parallel hybrid, which is short term, you'll be hearing more about that. And that's where you put an electric motor on the same shaft that's spinning a fan, and you still have fuel, jet fuel powering it, but you can reduce the size of the engine, and there's other benefits to it. And then longer term, the next phase, where maybe we are getting comfortable now with decarbonizing aviation at this scale, with these changes that at least the customer won't see. Once we're comfortable with that, we believe then that turbo-electric type technologies, where now you can make slight changes to the airframe, like boundary layer ingestion and some of these other technologies, which can boost you another 5 or 10% in fuel savings. And so these are kind of the two areas we're working in terms of combining electric machines with current technology. The other new area, safety and certification is a really, really big deal. Especially when we start talking about a whole new set of technologies operating at voltages. Today aircraft are designed for 270 volts and below because of Passion's curve. And now we're talking about 1,000 volts and higher to make them lightweight enough. Well, it turns out that if you're going to use all of that power at high voltage at altitude, it's like an arc welder, and in a millisecond you could arc weld through your frame of the aircraft if you're not careful. So right now, today's technology can respond to a fault in about 500 microseconds to 1 millisecond, which is enough to protect the airframe and protect people, but it won't protect the equipment. The equipment, like all these IGBTs that are flying at altitude, can be run at saturation for about 10 microseconds. So that's what we're doing next, is developing a new class of fault management hardware that can respond much quicker than today, but at those higher voltages and higher currents. Thermal management challenge, I alluded to this earlier. People are looking, well, what do you do with all this heat that you're generating on the aircraft now? So maybe your aircraft is more fuel efficient, all right? But now you have more distributed heat sources that are located throughout the aircraft. And it used to be we would just essentially dump all the heat either with ram air or out the end of the nozzle of the turbofan. That's where your heat went. But now we have a lot more heat, and low temperature heat's the worst kind of heat because it's very difficult to get rid of a low temperature heat. So where do you dump it? Fuel on these aircraft are limited to about 50 kilowatts. If you dump it out to the skin, which requires changing the aircraft design, you're limited to about 300 kilowatts. If you use ram air, which they do now on the Boeing 737, for example, or bypass air, which is the propulsive air from the turbofan, then you have drag penalties. In particular, we have to design for worst case, so like a 1% hot day. You have a 3 to 5% drag penalty trying to manage the heat. So you might develop all these other technologies, and then you find out, okay, now we have to manage the heat. Well, we just lost the benefit that we got from putting all these really slick new technologies on the aircraft. So that's what I mean. It's a systems problem. Energy storage, some other speakers might talk more about this. It's just not an option for single aisle aircraft to have it all electric aircraft. The battery size would be bigger than the aircraft itself. Even with the next 10, 20 years of technology improvement. In fact, we're assuming you need about 500 watt hours per kilogram, specific energy density for batteries, just for the parallel hybrid to really close in a good way. And we're banking on that as well. So these hybrid solutions are really a compromise because we don't have the battery technology where we want it to be. So when we use that word hybrid, what does that mean? That means we're keeping really all of our other technology, and we're adding new technology onto the vehicle as a compromise, which makes for very complex systems, more complex than they are today. So again, it's not easy to get fuel savings on these large aircraft, and we're making the problem more complicated because of all the new technologies. Eventually, it should all get simplified again, but that's where we're at today. Oh, and I should just mention that, jet fuel, 40 times, 50 times lighter than a battery for the same energy storage. But Department of Energy, RPE, are looking at, synthetic fuels, carbon neutral fuels. So that might be another path. And I think one of the other panelists might talk more about that. And then I talked about materials kind of being a technology that can elevate everything else up. And so we are working superconducting materials. Main challenge there, and keep in mind, we're trying to make things very efficient and very lightweight because we're adding additional, it's just like adding additional cargo to the aircraft. Ideally, we'd have 100% efficiency and no additional weight. That's what you'd like to see, but that's not the case. So we're adding technologies, and then we're using, so we want to minimize the efficiency impact and minimize the mass impact, which on its own would actually make the vehicle less efficient and make it weigh more. But the reason for electric aircraft and what it buys you are other approaches that you can get. It's usually airframe related improvements, or you're improving the engine efficiency by increasing the bypass ratio. I know I'm throwing a lot of concepts all at once, but the superconducting materials allows you to make electric machines and distribution systems that are much lighter potentially. But the problem is that AC is not managed well. So DC current's fine, but AC is not. So that's one area we're working, is how do you make AC still be close to superconducting performance. Insulation materials, we have all this new heat sources. Normally insulation materials also hold in heat. Well, we need insulation that can handle high voltage and conduct heat at the same time. Magnetic materials. It turns out that if you're going to be building filters and other electrical parts and pieces, you like to go to higher frequencies because that reduces the mass. Typically, you end up with hysteresis losses and other losses that reduces the efficiency. So we're developing new materials that can handle higher frequencies. And then also just, not even at superconducting, but just ambient temperature conductivity of materials. The higher conductivity we can get, the lower the mass can be. And then, so you have all of these different technologies, and at the megawatt scale, and testing them is a challenge. So we put together an electric aircraft test bed back in 2015, and it's actually been helping industry quite a bit at this point, because we need to test at megawatt scales and all of the system interactions. So for example, I give a list down there, and all of this has to be tested at altitude, so 35,000 feet, because different things happen at altitude. So for example, voltage, as you go higher up in altitude, you tend to get partial discharge. Thermal management systems, because you have thinner air, the heat transfer coefficient changes, and so forth. So everything has an altitude-related response, and so you want to test it at altitude. But you want to test high voltage bus architectures, high power megawatt motors and inverters. You also want to be sure that your communication systems can still work properly, because now we have all of these high power systems next to your communication systems. You still want to try to meet the standards that are out there, the DO-160G and other standards. And I mentioned earlier the fault protection. We need faster fault protection, and then system thermal management. So we have an altitude chamber that's about 25 feet in diameter and 20 feet high and megawatt scale, and can handle a megawatt worth of heat. And so just in conclusion, and in the panel discussions, I can answer more details on any of these things. But I guess the bottom line is that I think where we're at today in terms of megawatt scale technologies for single aisle aircraft we've actually confirmed, I believe, that motors and inverters at the megawatt scale can be light enough, can operate at those higher voltages, and the only thing left is confirming their durability. But there's very little public information out there about it, because it's a competitive market right now. But we think those are actually addressed. We think those are you're going to be hearing more about those. The new area that needs development that we're working right now is the system level technologies for those things. So propulsion controls, faster fault management, and integrated thermal management. And again, doing it without adding too much more weight or complexity to the system, and still finding a path to be able to certify all of these technologies. There's multiple government agencies that are collaborating in all these areas. But again, the bottom line is large transport aircraft has the biggest impact on CO2 production. So this is where we're tackling, and it has the highest impact on decarbonization. And then in addition, there's new mission capability that's possible because of it. Like, for example, taxiing on the ground at the airports could be done electrically, and it'd be quieter, and there's other benefits to it as well. So it's a system thing, but it's also easy to have one part of the system disproportionately affect another part in a way you didn't expect. And then I'll just conclude with the challenges to having this be adopted, beyond showing that the technology works, it's developing and working with FAA and other organizations to develop operational and certification requirements. And it's kind of hard to certify things until they're flying and you can confirm that they perform as you expect. It looks like we can meet the existing EMI standards and flight management standards. And then dispatchability and infrastructure, any changes we need to do. For example, if we're going to have energy storage at airports, then we'd have to put in if you're not going to charge it with the vehicle itself, you might have to put in charging stations and things like this. But overall, in the past 5 years since I've been working on this area, we went from, we have no idea if it's possible to, it actually looks like it's very possible, and we're going to be doing some flight demos in the next couple of years. That's it.
Thank you so much, Rodger. That was a tour de force of many things, lots of opportunities for material scientists, mechanical engineers, electrical engineers, lots of fun interdisciplinary engineering to be done. Next, I'll transition over back to Stephen, who's going to tell us a little bit about alternate fuels and then another exciting strategy for electric propulsion, which is a little different from what we've been hearing.
Thanks. Yeah, so I thought I'd start by giving a high-level view on what the mitigation approaches are to address aviation, not only CO2, but also the non-CO2 effects I mentioned that gives you roughly a factor of 2. Then I'll move to some of the challenges unique to some of the future applications of drones and urban air mobility. So at least for commercial aviation, mitigation approaches include operational, which means flying planes more efficiently so they burn less fuel. That's something we've got to do, but it might only give you something like 10%. So it's important, but not really gonna get you to something close to net zero. Secondly, fuels. So you don't have to just use petroleum-derived kerosene or Jet A or Jet A1 fuel. There are other options. Third, technology, which is what most of this discussion will be about, but there's discussion there. And also fourth, economics. So there are approaches where you could price in carbon into the aviation system and internalize the environmental impacts that way. But first of all, I want to focus on fuels. And in particular, I want to talk about biofuels, which the idea behind a biofuel is to use biomass, which means a crop or a plant or a tree or something, to make jet fuel. And of course, when you grow some biomass through photosynthesis, carbon dioxide is taken out of the atmosphere, and the biomass that's created is physically carbon and oxygen and other components where the carbon came from the atmosphere. Then you convert that biomass into a fuel with chemical engineering techniques, then burn it. And the carbon atoms in that fuel came from the atmosphere in the recent past. So the idea is that the life cycle, as it's called, carbon dioxide emissions of a biofuel is significantly lower than a conventional fuel. Now, there are many ways to do this. You can have a whole range of different kinds of feedstock, as they're called, crops shown in the top left here, like soybean or camelina or jatropha. Then there are techniques such as producing heifer fuels by mechanical and then chemical engineering approaches. And then there's a whole raft of different types of feedstock, meaning crop, that can be used to create fuels using a whole range of different techniques, including fermentation and Fischer-Tropsch. Now, all of these different techniques are something that at MIT we've gone through over the last 10 years and assessed the life cycle greenhouse gas emissions attributable to each of those different biofuel pathways. So what this chart here shows is life cycle greenhouse gas emissions on the bottom, where about 90 grams of CO2 equivalent per megajoule of jet fuel is about what conventional fuel is. Then on the y-axis, you can see a whole range of different biofuels where we've assessed the life cycle emissions associated with creating those biofuels. And you can see there's a lot of biofuels that give you reductions in terms of life cycle CO2 that are 50%, 80%, and sometimes more. So what this tells you is that biofuels really are a viable way to reduce CO2 from aviation, but there are some downsides, including that they cost twice or sometimes several times more than conventional fuels, and they can, in some cases, have issues associated with competing for land with food crops and other land use change related issues, but potentially an important part of the mix as we seek to solve this problem. So let's go on to technology then. Well, on the technology front, there are a number of approaches. I'll highlight a couple here. The sort of most common approach is to think about decreasing the fuel burn of the vehicle. And that's obviously what we're talking about most of all, probably the most important single thing to do. That's really about saying you want to create a vehicle that uses less energy. Beyond that, you could say, well, beyond conventional fuel or even a biofuel that looks chemically very close to the conventional fuel, you could go for a very different kind of energy carrier. For example, a cryogenic fuel like liquefied natural gas or like hydrogen. Those have some benefits and disadvantages that we can talk about in the panel session afterwards, and I see some questions coming up on that to go off from there. And then, of course, fully battery electric aircraft could be a solution in particular for very short haul and urban air mobility, where they look more viable based on where we can see the battery technology going. But if I mention the lower fuel burn, colleagues in MIT's Aeronautics and Astronautics Department, in collaboration with Pratt & Whitney and Aurora, a few years ago designed this aircraft called the D8 or double bubble. And in the more extreme technological assumption scenarios for this aircraft, it could yield up to a 70% reduction in fuel burn using a range of approaches, including boundary layer reduction. Now that sort of, that really does move the needle in terms of getting us towards net climate neutral. And you can imagine that if you had an aircraft like this, perhaps combined with biofuels, those two things together really could get you a long way towards a climate neutral aviation sector. But what I thought I might change to now is to look at a different application from commercial aviation and think about drones. Now, drones, and which are kind of similar in size and range in some ways to urban air mobility, have been around for a long time. This is an example of a military aircraft that's been flying for some 20 years. There are also other applications more recently, like this blood delivery drone used in Africa at the moment, and perhaps in the future things like Amazon Prime Air and urban air mobility at a slightly larger scale. Now, while at a global scale we worry a lot about carbon dioxide and energy use, when we get to the more local scale, we have pollution emissions that we're concerned about, energy use still, but also noise. So in order to enable local scale aviation, meaning both package delivery and other services, as well as potentially air mobility, we need to solve those challenges. Now, all of these things have rotating propellers that create a lot of noise. And one possible approach we've explored at MIT is to say, well, can we fly a plane without using any moving parts and get rid of the propellers that create the noise? So the idea is, can we use electro-aerodynamic effects to create a near silent solid state form of propulsion? So the physical principle is pretty simple. You have a very high voltage electrode here on the right and a very low voltage airfoil. When you charge that ionizes nitrogen molecules around the high voltage electrode, which then there's an electric field going from the high voltage to the low voltage that attracts the ions towards the low voltage. Those collide with neutral air molecules, transferring momentum to them, creating a wind or an ionic wind in the air, and that's the mechanism for producing a propulsive force. So over the last about 9 years, we've done a series of experiments at MIT to build up the scientific knowledge base on how these kinds of ionic winds, as they're called, are generated and how efficient they are, and eventually designed a small 5-meter wingspan airplane shown here, which, if you zoom in under the wing has an array of these solid state propulsion systems with emitting surfaces that emits ions that then get collected on these airfoils. This was flown for the first time just over a year ago in the MIT gymnasium. So that was the first solid state flight of an airplane with no moving parts. It only flew 60 meters and for 10 seconds, but we've got to start somewhere with these things. And just to prove that wasn't just a launcher, this is how it looks when you don't have a powered flight. Taking those 10 test flights together, we've got a chart here of altitude versus distance for the powered flights versus unpowered flights. And it does show that we did manage to sustain a steady level flight for this solid state propulsion aircraft. Now, going forward, we're working towards newer designs and are working to design an outdoor plane that will fly for some 30 minutes with a small payload. And this is a long way from being useful for package delivery, let alone air mobility. But there is at least some potential here for creating a whole new form of propulsion that could be useful in some special applications. So with that, I'll hand back to Venkat.
Super, thank you so much, Stephen. And then finally, we'll close out with Ed again. And I think I'll give Ed the opportunity to rebut to the common statement made on the lack of technological progress, right? We wanted flying cars. We got 140 characters, or I guess now 280 characters. So Ed will showcase what his team has been thinking about on building flying cars. Unmute yourself, Ed.
There we go. Do you see my full screen again?
Yep.
Okay, great. All right, so I'll move on to the next chart. Yeah, so this dovetails a bit with Rodger's list of some of the challenges, and they come in a few buckets, just really as Rodger also said. There are some technological limitations that are currently today limiting us in terms of payload and range. One of the things that is obvious to those in the aviation industry, but maybe not to everyone, of course, is with these liquid fuel traditional aircraft, the fuel weight goes down as you move forward in flight. If you're talking about all electric battery systems, you're carrying that weight for the entire flight. So that's right at the start an additional impact beyond just the basic energy density. Once you start talking about urban air mobility applications, now you're talking about vertical takeoff and vertical landing, which adds a pretty significant peak power event, both at the beginning and the end of flight. And as you can imagine, that peak power at the end of flight is at the lower end of state of charge of the battery. Temperatures have risen. This is a pretty stressful environment for a battery. Then, of course, when you're talking about multi-rotor systems that are pretty typical for urban air mobility, there's a whole distribution design challenge there. But even moving just beyond the technical challenges within the subsystems of the vehicle, there's other issues to be solved in developing the urban air mobility market. Because this will involve a number of different industries creating new businesses or using their businesses in new ways in order to make this a reality. As you can imagine, trying to develop the landing and takeoff vertiports in major urban centers, there's a whole new element of regulation and certification that is going on that Rodger touched on. These are all new technology systems. The FAA has a structure for using special conditions to move these new types of systems through a process. But again, a lot of the elements will be new that are part of that process, and the means of compliance are part of the challenge that folks are developing now. Big infrastructure issue, as I mentioned, in terms of vertiports. There's obviously identifying the land, working with landowners, bringing the electric infrastructure to that location. And then the last piece also is the integration piece. So even after you've solved some of the subsystem and ecosystem elements, putting them all together needs to end up, when it's at scale, with a business that makes sense financially. So we look very carefully at developing solutions, not just for initial performance, but performance over the life cycle of the vehicle when it's in scale operation and scale business. So I'm going to zoom in to, of course, for urban air mobility, one of the key challenges, which is really centered on the battery. And it's already been remarked how the energy density of batteries is substantially different than traditional fuels. But I do want to give some level of hope. Battery systems, mostly through development through the ground vehicle sector, have gotten to a stage where there's enough capability that we can start to develop vehicles, and you've seen a number of different vehicles from different companies that are in flight tests that can do a reasonable radius of operation. And obviously, as that continues to advance through time, we're going to see that sphere that they can operate in start to increase. But again, not a simple problem. Many things need to be included beyond just the simple chart that you see in front of you. There's how the power profile versus time works for the different mission applications. There's the issue of reserve energy that needs to be addressed. There's the issue of degradation that needs to be addressed over time, fault tolerance, and what we refer to as packing factor, which means your battery pack is more than just cells. The packing factor is typically for a state-of-the-art large battery pack like a Tesla vehicle, somewhere around 70%. And the rest of that is bus bars, interconnections, sensors, thermal management systems, casing systems. So all of these end up impacting the size of that radius for an urban air mobility vehicle. The last thing that I'll just mention on this chart, though, of course, is as you move to some of these advanced technology cells that are in the laboratories, that pilot samples are being made available today on, those need to have a market for those to advance and be commercialized. So there's a bit of a horse race going on as these new markets develop. They provide an opportunity for a marketplace for some of these advanced cell technologies. One of the things I often contrast between the ground automotive vehicle industry and the electrified aviation industry is, if you're weighing different attributes that they're focused on, once you get to a certain energy density for a passenger vehicle, a car in an electric vehicle, you've gotten it to a point where it's at least 300 miles of range. I will say we're not quite there yet for some of the larger vehicles, but we're getting there. And the other big thing that they're, of course, focused on is the cost and the fact that there's single ownership for maybe a 6 or 8 year lifetime of the vehicle. If we're talking about sort of relative attribute focus, in the aviation side, the highest focus, of course, is the safety mark. We can't operate our vehicles at reduced power if we have to degrade some of the batteries or cells or modules within a battery system. We can't pull over to the side of the road. So safety becomes the sort of the first priority in terms of how we architect the energy storage system. And then below that, right below that, of course, is gravimetric density. In a vehicle, a consumer vehicle, one of the driving factors is typically the volumetric density because of the size of a typical consumer vehicle. Our biggest focus is really the gravimetric density, and it's particularly acute for these electric vertical takeoff aircraft, which have that peak power transition at the beginning and end of flight. So those are some of the key things that are driving our investments and driving investments across the industry in order to increase the size of the available market for these urban air mobility vehicles. And I'll just touch on one other theme, which is really coupled to the battery system. Obviously, there's a coupled thermal challenge, which Rodger talked about, and in the urban air mobility sector, as I mentioned, I think a little bit earlier, as you get to the end of that mission profile, you have a peak power event during the transition and landing event. This also causes a limiting thermal event and thermal management challenge for the urban air mobility vehicle designer. Obviously, you then have to trade off weight and reliability of different thermal management systems, and you need to think about this in how it will manage single fault conditions and be able to accommodate single fault conditions in operation. And as Rodger talked about, it only gets worse with scale. So as you start to look at some of these larger aircraft applications, the dimensions of the thermal management issue just become that much larger. And in terms of design paradigms, we typically focus on first reducing the amount of heat that we're producing, and then two, trying to reuse that heat or those losses as much as possible. And those are really the two levers that we have beyond some of the new materials that are being developed, as Rodger also mentioned. So that's really kind of the key item that I really wanted to focus people's attention on for this urban air mobility market. And thanks. I'll turn it back to you, Venkat.
And thanks a lot, Ed. Very exciting to see the progress in UAMs. Okay, so we have a few questions. We want to try and get through as many as possible. One of the things that's probably on many people's mind is we're going to return to hopefully a new normal and what that looks like for aviation. So I'm going to put Ed on the spot and allow him to take a crack at this.
Yeah, so I would probably be quite wealthy if I was able to predict how that is going to be. To be honest, nobody knows. If somebody tells you they know, as I think the first keynote speaker said yesterday, that they're not telling you the truth. But I think for sure we are going to see some kind of reshaping of how people travel, whether that's on the ground or in the air. And that's, of course, one of the sort of high-level aspects that the Boeing Next team is very much focused on, is thinking about new ways that people are going to travel and all of the different stakeholder issues that might be driving or pushing that in one way or the other. So all I can say is, believe me, we are thinking about it, but we don't have a crystal ball about how that's going to change.
All right, super, thanks, Ed. So this is probably for Rodger. There's a question around lower capacity markets, so long haul skinny markets or regional markets as an alternative to driving, which is the only option in some cases. Any thoughts on whether that is going to grow? What does that look like?
So it's interesting because, wearing the NASA hat, federal government hat, I'm actually privy to a number of startup companies that are actually don't want to be disclosed at this time. And there are some very exciting technologies. So the first message is there are actually actively flying vehicles that have not been in the news yet that I think are going to potentially serve that market and be surprisingly competitive with an automobile. I know I wish I could give more. But yeah, NASA and other organizations are looking at the use of regional airports, 20 or 30,000 new locations. Zunum was a company that was going to tackle that market, and they didn't. Their fundraising didn't work out for them. There's also been some challenges. Aviation has had an accident. there's a number of new startups, because these are systems of systems in a new paradigm, that, you know, even the test flights they're having some challenges with. So so that's where we're at right now as an organization, is how do you make this safe, certifiable, you know, long endurance, and, you know, and then the companies are trying to make it be cost effective. So before I would start dreaming, you know, about what's next, I want to be sure that the technology is going to be there for us.
All right, thanks a lot, Rodger. I'm going to pull Stephen in. This is a question that was partially answered in chat, but I think it's a question that's worth reiterating on, which is the opportunities around hydrogen, either in direct combustion or fuel cells. Stephen, do you want to just elaborate on your answer here?
Yeah, I think hydrogen is something that we really need to look at in some real depth again as an industry. I mean, it was considered some decades ago and kind of ruled out. So there are problems with it. In my mind, the single biggest problem is that you need a way to sustainably produce the hydrogen. Otherwise, there's no point. So you know, we need advances in sustainable hydrogen production. And unlike conventional fuels, you can't mine hydrogen. So it's going to be electrolysis or some other approach. And say if it was electrolysis, then you need to have a clean grid. So there's not much point doing it in the US right now, where there's so much coal and gas on the grid. So there's also a coupling there with the grid. So let's say you solve the sustainable hydrogen production and could do it in a reasonably economic way. Then it starts looking pretty good, because you could definitely burn it in a gas turbine. It wouldn't need huge modifications from current gas turbine technology. Different injectors, sure, but I mean, people have run gas turbines on hydrogen. That's possible to do. There would be challenges around having a cryogenic fuel on an airplane, safety challenges with crashes and things. Then you also have the sort of aerodynamic challenge of the fuel being better in terms of mass energy density, but worse in terms of volume energy density. So you'd end up having to have more volume for fuel storage, and that would give you some disbenefits in terms of the aerodynamics, depending on how and where you stored it. But it's not as easy to squirrel away in the wings as is the case with conventional fuel. There could also be some environmental challenges. So while you might see benefits in terms of reduced particulate emissions, it's quite likely you'd have more contrails being formed, which are these artificial clouds, and that's because the water vapor emissions from hydrogen would be much higher. So it's not entirely clear how the environmental balance might work out. But overall, I think it's an important thing that we need to look at again. Huge amounts of challenges, but technically possible. Environmentally, the jury's out, and whether it economically hang together, jury's out as well.
All right, super. Thanks, Stephen. Maybe this one is for Ed. Things around maybe for Ed and Rodger around regulation in UAVs, with UAVs flourishing everywhere. You know, what are sort of the ways in which we can ensure that proliferation is a good technology base and does not devolve into something that I guess turns into a nuisance?
Yeah, there's kind of a wide open answer to that, I would guess, but you know, like with any kind of technology, needs to be, you know, very carefully thought out, both from the standpoint of the developers and as well as the societal groups, whether that's states or federal level, on how they can potentially be used or misused. I think we've already started to see over the last couple of years some of the very good ways that UAVs can be used beyond just being a 400-foot selfie stick. And, you know, I think as those are starting to gain traction and gain basically a demand, that's where the businesses are going to be focused on producing solutions for. Thanks.
All right, so we're running against time, almost to the next panel. So let me join in thanking the panelists and the audience for engaging. Awesome set of questions, and thanks a lot to the MIT team to pull this together in this period. It's been difficult, but I think it's an exciting panel that we got together. Thanks.
Thank you.